So this short video is to explain activity 3 in Spotted Owl model. And in this activity we're going to look at an actual model that was written up as part of practical research. Here is the paper. Let's just skim this paper. It's talking about spotted owl. And this one gives a somewhat more complicated model than the one that we've had, but there's a lot of similarity. Now, in this model, in this paper, it explains where the model comes from. And let's see. The paper also gives some parameters that the model uses, and that's important for what you'll have to do. I call your attention to this paragraph here, where certain parameters in the model are given. You can see here the system diagram, which is very similar to the system diagram that I gave previously. Let's take a look at that so you can compare. I think it's actually here. Now in our system diagram we had juveniles, subadults, and adults. And we had this pattern of kind of this cycling pattern here. Now, as in his model, it's a little more complicated. Instead of juveniles, subadults, and adults, he says juveniles, singles, and pairs. So he actually includes the male and female in this model. And there are some more lines in this model than we have in our previous model. Here you see juveniles can go to singles, but singles can actually remain single. Singles can pair up, pairs can become singles again, pairs can remain pairs, or pairs can go to juveniles. So here we have a somewhat more complicated structure, but it still is the same sort of idea that you have different compartments, if you will, and from time to time, individuals in each compartment will either move to another compartment or give rise to another individual in that other department. For instance, a pair doesn't become a juvenile, but a pair gives birth to a juvenile. Okay, so let's go on here. Here's some curves here, and some of his results. Now I'm just going to cut down to the model itself. He gives the model itself in the appendix. And here it is. So I'll show you in my own paper here. I reproduced the model down here. So these are the equations that he used. And there are reasons behind all of this. Dispersal survival. In his model, the juvenile males go out to find a site to rest, to wait for a female. And this equation looks a little bit complicated, but what this is 1 minus the probability that the male will fail to find a site. In other words, the probability the male will survive is 1 minus the probability that he'll die trying. And some of these are intuitive. The available sites for an owl are suitable sites minus occupied sites. I should mention that in this model, the pair of owls takes up a site. The male's there first, and then the female finds the male. But they need to find an independent site. They can't have overlapping territory. These birds are very territorial. So available sites, it's pretty obvious that they should be the number of suitable sites minus the number of occupied sites. And notice that all of these parameters are functions of time, because the available sites will change as a function of time. The occupied sites can either be occupied by a pair or by a male single. There's a problem with this equation. This should be 1 minus here and 1 minus here. This is similar. Mating success is computed as 1 minus the probability of mating failure. This term here is the probability that a female owl will fail to find a male. And then we have these equations here. Now notice until this point, the available sites depend on suitable sites at the same time. Okay? This dispersal survival actually should be dispersal survival as a function of t. Okay? the parameters depend on other parameters at the same time. But if you look at 5 and you look at 7, in this case, the number of male singles depends on the juveniles and male singles and pairs at the previous time. So this is reminiscent of our previous model, that the previous time determines the future of the model. Similarly, the pairs. The pairs depends on the previous time. Now for juveniles, he uses pairs at the same time. That's just how he does the model. All right, so be careful where the parameters depend on the same time or the previous time. Now, there were some errors in these equations, which I've corrected. That for mating success, he forgot this parameter as a function of t. The total sites doesn't change, so I don't put that as a function of t. Notice also that dispersal survival is a function of t. He didn't actually mention that, but it is true. Equation 5 has some things missing, some sort of a misprint, something's not clear. So I improved that. And 7 also. Let me see if there's anything else I need to mention. No, I think I got everything. So what you need to do is create a spreadsheet. Here's an example for you to follow. If this is too small, you can blow it up. Where's my zoom? You should be able to make it big enough so that you can see the headings here. Here are the parameters that you'll have to enter in, and as usual, I made a little box for the parameters. These values you can look up in the paper. Okay. For these other quantities, I suggest you arrange the columns like this. Time, the time is measured in years. The suitable sites is always a constant. Then you start out with singles, pairs, and juveniles. These values you can put in as 0, 25, and 0. You can just put those in. Then these other values here will be equations depending on these values here. And so I want you to implement these equations up here. Well, I'll give you one example, say for instance. Let me give you the number, let's see. Well, let's just look at number 1, dispersal survival. Here it's 1 minus parenthesis, 1 minus available sites at t divided by total sites to the nth power. So let me go to my actual spreadsheet here and see what that looks like. So let me blow this up so we can see it. So this was available sites. If I go here, you can see that it's, whoops, let me see what I'm doing here. Dispersal survival. Let's look at dispersal survival. Dispersal survival I put here. And it's 1 minus K4. You'll have to look at what K4 is. K4 is the available sites, divided by B8. B8 is the total sites. Okay, I have that hidden. I want you to put the value in. And then that's raised to the power of B2. B2 is this value of M. Okay, so that's exactly the equation that's given here. Dispersal survival is 1 minus parenthesis 1 minus available sites divided by total sites to the nth power. Okay, so you should be able to go through and put equations. I should mention that you'll need, you put values here, here, and here. And then you put equations for mating success, occupied sites, available sites, dispersal survival. Then in the second line, you'll need equations for singles and pairs. And then the equations that you have in the, and also for juveniles. And then the equations in the first line that you've already created, you can fill down to the second line. All right, so once you've, let me just show you this. I'm going to erase this part. I want you to go down to time 50. So I'm just going to go ahead and erase this. Now, once you have two lines like this, you can just grab your second line like this. And I do suggest a good way to select multiple cells is hold down the Shift button and use arrows. So I'm going to go over, select all the columns, then go down. I'm here and I want to fill down. Fill is here, go down, and I recover my values here. Okay, so that's how you do it. Create the first two lines of the table, fill down, and you can create the rest of the lines necessary. All right, now this part I need to erase because it went too far, so I'm just going to select this part and erase it. All right, so that's how you create the table, create the formulas for the first two lines, and then continue. All right, so let's look at the other problems you have to do. Okay. All right, now notice column F is labeled male, female singles. This is actually equal to the number of male singles and the number of female singles because the two are equal. Okay. And here I said you need to fill in the perimeter values in column B, so you'll have to look these up from the paper. I do want the columns down to give 50 here, so here you can just shows down to 25, but I want you to take it down to 50. System is not exactly a linear dynamical system. And the reason is that the survival probabilities are also functions of time. If you recall these arrows here that join the different compartments, these arrows themselves are functions of time. So that means it's not quite a linear dynamical system, but it's close. It's not too far off, and it has many of the same properties. All right, so where are we to now? Okay. All right, so what I want you to do here is create two or more columns in your spreadsheet and compute the ratio singles to juveniles and paired to juveniles for t equals 1 to 50. I'll show you what I did on mine. The two columns were over here. I did singles over juveniles and pairs over juveniles, two more columns there. And then I want you to plot those two ratios as functions of time, see what the graphs look like. Use your result from B to estimate the eigenvector. The eigenvector should have three components, one for juveniles, one for singles, and one for pairs. And I want you to find the eigenvector corresponding to the largest eigenvalue. Now remember what we've talked about, that the largest eigenvector is related to the trend. Okay, so you should be able to go and do something with it. The trends here, what you get will not look quite like this, but what you want to do something with the trends here to pull out an equation that you can use to find the eigenvalue. I won't say any more than that, but it's something that we've done already in the previous activity. Okay. So you can get an eigenvector for which juveniles equals 40. Now remember, if you take the eigenvector, you can always multiply it by a constant, and it's still an eigenvector. So I want you to take the eigenvector that you find and multiply it by a constant so that the juveniles component is equal to 40. Okay, and then the question about what happens when you do something, plug in something. And then here's also another question where you have to change the numbers. Okay. All right, now F and G are a little bit different. You're going to be using something different. It's called goal seek, so let me explain this one. Suppose now that the number of suitable sites remains constant at 400. At year 50, I would like to have 200 pairs of L's. At time 0, I'll start with X pairs, no juveniles and no singles. Use goal seek to find X. Okay, so at year 50, I would like to have 200 pairs of L's. So what that means is we're looking at year 50, which is, let's see, number of pairs is column G. Okay, so I'm looking at the number here in column G, and I would like that number to be 200. So what I need to do is go up to this formula here, and I need to find goal seek. And maybe it's here. I'll have to pause a minute and find it. Okay, I found it in this version of Excel under Data. It's under What If Analysis. Go here, and look for goal seek. Okay, I'm going to do a different number. Suppose I would like the number of pairs at time 50 to be equal to 50. All right, so that means I want the value in this cell to be 50. And then I need to tell Excel which cell I'd like to change in order to make this value work. So I'll click here, and it will let me select a cell. Now suppose instead of changing the number of pairs, I would like to change the number of singles. I want to add some singles in order that I'll have 50 at the last time. I actually think that's not going to work because it will give me a negative number. So let's go ahead with pairs. I want to change this value here to make my goal work. So then I just put there and press enter and OK. And it says goal seek found a solution. It changed the number of pairs to 14. And we can scroll down here to the number of pairs at time 50. And that's just about 50, what I wanted. So let's try this again, just to show you how this works. Suppose I would like this number here to be 45. Right? We go up to here to what if analysis. So I'll go to goal seek. And I would like that value to be 45. And suppose I want to get the 45 by changing the number of juveniles at the start. So I want to add a certain number of juveniles at the start to guarantee I'll have 45 juveniles at the finish. So I'll press OK here. And it found a solution. It turns out if I add 7.19 juveniles at time 0, then if I go down here, I'll have 45 juveniles at time 50. Okay, so that's how you use goal seek. You can use that for part G and also for part F. Okay, in part F, it's straightforward, pretty much like what I did. In part G, you're going to put in cell C1, you're going to put a ratio of successive numbers of pairs. And you want to use goal seek to find a starting number of pairs so that the pair population does not change from time 50 to time 49. Now, if the number of pairs at time 50 is equal to the number of pairs at time 49, then what is this ratio? I'll let you think about that, but this ratio has a very simple value. So that's your target value for cell C1, and you use that target value to determine the starting number of pairs. Now, he says try to find two different starting numbers of pairs. It turns out that goal seek looks around for a solution. It starts at the value that you give it. So you can, if you change the value here and you use goal seek, you may end up with a different final answer from goal seek. So try different initial values of pairs, put in some values by hand, and use goal seek to make the population of singles stable, and see if you can get two different stable populations. Okay, that's it. If you have questions, we can talk. Good luck, have fun.